Hi, here we are working a problem of vertical curve. We are trying to check the adequacy of the vertical curve and trying to assess if this curve is not adequate, what would be an adequate curve length. Now this is a crest vertical curve, so that issue is described here in the problem. It's an equal tangent crest vertical curve, and in this class we're going to typically be dealing with equal tangent curves. It's an 800 feet equal tangent vertical curve, so that means the length of the curve, L, is given to us as 800 feet. Measurements show that at station 3 plus 52 from the PVC, if you want to convert that into distance in feet, 3 plus 52 station will be 352 feet from the PVC. So PVC is the point of vertical curvature, which is where the curve starts. The vertical curve offset is 3 feet. So immediately, by reading the sentence, the vertical curve offset is 3 feet, you should know that you need to be applying the vertical curve offset equation. So the offset equation is given here. Y is equal to capital A over 2L times x squared, where y is the offset at any distance x. Capital A is the absolute value of difference in grades. L is the length of vertical curve in feet, and x is distance from PVC in feet. Now you know this is the distance of PVC in feet. So what would that value be? 3 plus 52 station. That means this value would be 352 feet in this problem. What else do we know in this equation? We know the length of the vertical curve, it's 800 feet. Capital A, absolute value of difference in grade. Do we have any indication of what the grades on this vertical curve are? They are not given at all. So we don't know anything about this capital A value, because if we don't know the individual grades, we probably don't know capital A as well. Maybe we do something about that. Maybe we do know something about that, but we'll see. And the y here is the offset at any distance x. In here, I probably should draw this y as a small y. So I'm going to make that a small y. It's the offset at any distance x. So based on this equation, what can you find out? What can I find out if I plug in the numbers that I have available here in this problem? I'm going to plug in y is equal to 3 feet, because the offset is 3 feet. So this is given to me as 3 feet. So I know 3 feet, and I don't know capital A. I know the length value, which is 800. And I know x will be 352 whole squared. And I can solve this parameter, or this equation rather, for capital A. So if I were to solve this equation for capital A, what I'll get is 0.0387, or I can say 3.87%. That means my capital A value is 3.87%. Now, knowing this A value is critical, because we know how do we assess the adequacy of the vertical curves. We do that based on the capital K value, that is nothing but L over A for any vertical curve. So what we're going to do now is we're going to consult with the AASHTO table. We're going to find out what the minimum required value of capital K is for a given design speed. And if the value that we have here in this problem, or in this particular vertical curve, is that adequate for that kind of a speed. So here we are going to go into the next slide, try to calculate the capital K value for this curve and compare it to the value that is prescribed by the AASHTO Green Book. So let me bring up the table from AASHTO. Here is the table from AASHTO. The design speed that's given to us in this problem is 60 miles per hour, and we want to test it out. What is the requirement for a vertical curve of this kind at 60 miles per hour? Now the question is, we have two parts of the table. We have the design speed, we have the stopping side distance, and then we have the rate of vertical curvature, capital K value, This is what you're trying to look at. Now you are given crest curve, table for the crest curves and sag curves. And if you look up this table, what kind of curve we have in this problem is an equal tangent crest vertical curve. So I'm going to be looking at this part of the table and not this part, sag vertical curve part of the table. And if you go to the 60 miles per hour design speed, the stopping side distance is 570 feet, but the K value that is required is 151. Now if you remember, the K value that's derived, capital K value is derived by L over A measured in percentage. So when you measure the value A in percentage, you can just do length of the curve divided by capital A value and find your K value. So in this problem, the K value that we have for this curve is going to be 800 divided by 3.87. And if you were to calculate 800 divided by 3.87, that value is about 206. Now the question is my curve adequate for 60 miles per hour design speed? I would say that it is, because the K value here is 206 and the Astro tells us that the K value that we require is about 151. In fact, just this curve itself is probably okay for even a 65 miles per hour design speed. Question is it okay for 70 miles per hour design speed? The required K value is 247 and we only have 206 K that is in the field. So that means this curve is not adequate for 70 miles per hour design speed, but it's certainly okay for 60 miles per hour design speed because the required K value is only 151. So in this problem, my answer will be yes, this curve is indeed adequate. Thank you. I'll see you next time.